All right, hi all. Welcome to Chapter 2, Statistics in Practice. This chapter has two parts. The first part is called Observational Studies. The second part is called Controlled Experiments. So we're just going to go through some of the concepts and key points in this. Observational studies. So an observational study compared to a controlled experiment would be one in which you simply observe what's going on and don't manipulate it or add any kind of control elements at all. It requires a lot of, data gathering, observation, but also inferring a lot of the meaning behind things. So for whatever reason, we've got uncontrolled variables, maybe based on maybe it's a medical type experiment, and any kind of randomization effect might violate some sort of ethical principle. There's not a way to add influence to the situation, or there's just an impracticality there. Those are reasons why you might have a observational study rather than trying to create the experiment from scratch. One thing that you're not going to have in an observational study is finding a causal relationship. So you might identify a couple different things going on, but you're not going to have enough statistical evidence to say that this specific thing causes this specific event. So you've got a cause and an effect, right? That's causality. You can't say for sure that whatever happened is a result specifically of that, because there's too many other outside influences, again, because it's not a controlled experiment. The goal often when you're doing statistical research is to try to find that out. And instead, it's more of a not a determination of it, but just kind of a reporting on what you see, reporting on what is going on, and making inferences about it. But again, you're not going to have a statistically sound result on a specific cause and effect. Why might we do that? You know, in medical field, you might look at benefits and risks of various practices. Through your observation, you might be able to form a hypothesis, which then could lead into a controlled experiment. Gathering data in general to inform some sort of other real world practices in a clinical setting or in whatever other setting. Again, the challenge there, you're trying to draw an inference from what you see, but not applying your own biases. It can be tricky. There is a placebo study that they're going to talk about here, wherein they basically observed whether or not what the results of this placebo effect might be. In this specific study, they call it, what was it? Clofebrate. So clofebrate was a drug trying to determine trying to treat coronary heart disease in men. So in this instance, a number of people in the experiment were given the actual drug, clofebrate, and then the rest of them, half and half roughly, were giving a placebo, just something they're told this may or may not be the drug. Both groups are told this may or may not be the drug, maybe the placebo, or they're all told that they have to begin giving the drug, depending on the type of setup there. And then you observe the effects on them to see if you can try to find out if the drug is worth pursuing as a possible fix for the heart disease or whatever other ailment you're trying to solve via some drug trials. So some key terms to know here as we go into that: placebo is just any inactive substance, something that, it might be sugar water or something to that effect. Where you're not giving them an actual drug. Placebo effect is something that tends to show where a group has some sort of has some sort of result, some sort of effect, despite it not actually being the drug, simply because people get their hopes up, and the body can do odd things when it comes to thinking that they've got a better chance at curing a disease than not. It's that kind of, you call it maybe false hope, but it's real hope because the effect it has on the body, kind of an interesting phenomenon that occurs. So, kind of like laughter is the best medicine, some kind of just being in good spirits can be good for your body to recover. Reducing the stress. If you're stressed out about the ailment, you're less likely to recover quicker, but then you think that you have a drug that's working, then it does work, even though it's sugar water or something. And then another term to know when it comes to experiments is this regression to the mean. Sometimes you'll have a bunch of extreme sets of data, but then in a follow-up experiment, it's more likely to be closer to an average. If any of you guys are sports fans, you might see this when a particular player scores a lot of touchdowns one season, right? I'll give you maybe an example. A couple seasons back, Deebo Samuel of the 49ers is a wide receiver, but due to a string of running back injuries, had a number of just a really high volume of rushing touchdowns. I want to say it was somewhere between 11 and 14 rushing touchdowns on the season, which is quite a bit for a wide receiver. And then in follow-up seasons, did not have nearly that many rushing touchdowns. Regression to the mean, more likely that was an outlier and not something to be repeated. However, if you are a fantasy football person, you might have overdrafted a player who exhibits a season of just going crazy on stats. And then to find out that they are actually, more in line with what you originally would have expected them to be, which is still a very good player, very good stats, but not the extreme of the 22 to 23 season, 21 to 22 season. All right, so some terms to know when you're looking at experiments. So placebo-controlled observational studies allows you to add an extra effect to get maybe more significance to whether that drug is working. If everyone's given the drug and people are exhibiting various signs of improvement, are they improving because they think that it's working, or is it actually working? So the use of a placebo helps to control for that. Helps to give you a better likelihood of success. So you're not asking, does the treatment work, but does treatment work better than placebo effect, or placebo treatment, or no treatment at all? So is there improvement versus doing nothing? And that's the result you're looking for in that kind of test. Results of a coronary drug project. So based on the study, the survival rate they found was 2.5 times greater for those who adhere to their placebo, right? So the placebo itself had a psychological effect versus people who did not do the study at all. But was that the case? Was it the placebo effect, or because they maybe they were healthy enough to start the experiment at all, that they were just more likely to survive during the treatment period? Or maybe that people who were in an experiment are more conscious about their health, and so they are doing other diligent things. It's hard to draw an exact conclusion from it. And that's why it's not, you're not looking for cause and effect, you're just looking at more likely than not type of thing. And so it was not really a very successful experiment that they ran. It did not identify it properly, and using it, there was actually an excess mortality. The drug ended up being harmful to people. They didn't do all of what they could have or should have done in their findings, and then eventually the drug was discontinued. Sometimes there are variables that exist, and it's up to you to find them or eliminate them where something is creating a bias in the outcome. Something else unknown or data you didn't account for is influencing the dependent and independent variables, which is why this first term exists, which is peer review. Basically, you have a number of independent researchers evaluate what you've written to determine, is there any kind of shortcomings in the experiment setup? Is there a shortcoming in the findings? Did you misread or misinterpret it? It helps to cut down on the likelihood that published academic writings are nonsense or harmful in some way. Again, placebo effect, we've already gone over. Prognostic, so some kind of indication of something being known in the future is that term. I think you'll see that again coming up. And then confounding variable, so some other extraneous variable in a model that correlates, positive or negative correlation, with the dependent or independent variable. So either has an effect whereas one increases, the other is decreasing, or where one decreases, they both decrease, or one increases, they both increase. So some sort of correlation with that. And it's up to you to either eliminate that or determine what it is so that you can account for it in your testing. So here is basically you perceive a relationship between two variables, the independent and the dependent variable, but you completely misestimated that because you didn't account for that confounding variable. They also call that a spurious relationship between the additional variable. Types of confounding variables. So sometimes this might occur because of the, they call it operational confoundment, where the measurement instrument inadvertently measures something else as well. Situational, procedural confoundment. So mistakenly you allow another variable to change along with whatever it is you were manipulating or testing for. And then person confound. So this is where two or more groups are analyzed together. So you looked at all workers from two different occupations versus the one occupation you were really looking for. And so you've not accounted for the effect of those other variables on that other occupation, which has its own specific, maybe job requirements, job tasks that they have to do. You didn't, maybe you tested men and women versus just men versus just women. And so there are other individuals, individual differences that are not accounted for whenever you group multiple groups together. How can you decrease confounding variables? So in here we have ways by controlling for things like age, sex, double blind, where you randomize the studies and then randomize who gets the treatment, who gets the placebo. Randomly controlled studies where whoever you're studying is split up into you're not self-selecting, going out and saying, okay, you and you, but you have this bias where you're just selecting people of one race or people of certain height or weight or something like that. People that are wearing glasses or not, or somebody who looks closer to how you look so that you're more comfortable approaching them and asking them to be a part of the study. But just a completely random randomization to it will help eliminate some of that. There's an example here on this in graduate admissions, male versus female graduate admission rates. So let's look at a couple of the key terms going into this. Partition, you'll see, which is just whatever the segment is after it's been divided. That's partition. If you've ever worked on computers, you know that you can partition your hard drive into various subdrives. You could classify this portion of the hard drive as your C drive, and this portion is your D drive, and maybe you keep all your files on one, or your Windows operating system on one drive within the actual physical drive, and then you have all of your games or files on a different one. There's a paradox wherein if you take data from different groups and then you aggregate it, sometimes that whatever it is you found doesn't seem to be the case anymore, or sometimes all of a sudden a trend or a reverse trend appears when you aggregate it. So even though you have a very significant finding, when you look at individual departments, maybe when you look at the entire employment center of your entire operation, that data looks different. Aggregating just means that you are taking some elements, but you're considering it a whole. If you were looking at sales data in your retail store, you could look at the data of every single SKU of every item you sell, but when you aggregate it, it would just be sales, right? So that's a real brief explanation or example of aggregate data. So this bias that they showed was they published a paper showing when they aggregated all the data, it looks like the admission rate for men was 44%, the admission rate for women was 35%. So pretty clear bias of not allowing or approving women applicants for this college. Blatantly biased, right? However, there's more. When you look at it by department, what it found was there were actually a lot more applicants for so you had departments where there was just a high rate of admission, and you had fewer people applying for that. Basically, that the women applying were looking at more competitive departments, so the admission rate was lower. You had, Department E, for example, 393 people. Admission rate was pretty low to begin with. Department C, for example, there's only 30-something spots available, so 30-something people got in on both, but 200 more women applied for the position. So it's still about equal in total number of men and women who got into it, but they're a more competitive department. They could only take so many. Whereas it found that the men tended to apply to less competitive departments that had a high rate of admissions, engineering, chemistry. A lot more of them were getting in, but they were kind of going for the low-hanging fruit as far as just getting into it, right? So it turned out that the bias may or may not have existed after all, probably didn't exist. More easily explainable when we were trying for more competitive fields. So aggregating it looked like there was a clear bias. However, looking at it in the individual, perhaps not. So the question is, which should you look at, which would make more sense? And so it really is dictated by how what it is you're exactly looking to show, and that's where you have to factor in ethics into experimentation and reporting, and be completely clear on what your findings show. If you found both of those findings should probably be published, and not one more focused than the other. And then that could lead you to further writings in the paper showing more likelihood for women to go for more competitive fields. So now we'll talk about 2.2, which is controlled experiments. So this was looking at determination on a vaccine. A lot more people involved in this one. Double-blind study with a control group. So in this one, in the control group, there were untreated subjects in the control group. And then you had some that received a vaccination, random assessment of both, and this has now become the gold standard for clinical trial due to the overwhelming success of this polio vaccine. Not going to go into the science of polio vaccine, but make sure you read through probably this entire field trial to get an understanding of exactly what happened with that. Same thing with the design issues there, but just the way that they were able to ensure that there was no bias involved, that no one involved knew which ones were part of the control group until it was over, until after all the data was analyzed. But the data was recorded prior to knowing that, so there was no possible influencing on the outcomes or on it until after the data had been analyzed. This next study had to do with we call it a shunt procedure, a treatment for the liver, where there's some kind of bypass done for the vein. Not a medical guy here. And again, there was studies done with randomization and non-randomization to try to determine the effectiveness of it. There were some controls involved, which the specifics I'm not going to get into because I'm realizing this is going a little longer than I expected here. But steps here for random assignment of control. So start with a certain number of your subjects that you're looking to be part of the experiment. So let's say you have 20 people. Do some kind of randomization. It could be a random number generator, or you could just flip a coin. Everyone that flips heads goes in one group, everyone with tails in another group. And so you're not going to get exactly 50-50 because again, it's completely random. You don't know exactly how many are in one group versus the other. You're not specifically picking 10 people for heads and 10 people for tails. It does start to show that you might start looking for your top 50% of your performers versus looking at the performance of all people in the group. There's room for bias there. Scientific control, another key term you'll need to see, experiment or observation that designed to minimize the effects. So all of those types of things are in the realm of scientific control, trying to look at ways to eliminate bias, minimize any kind of other variables outside of what's part of the experiment. Typically, you're looking at a single independent variable and not multiple independent variables in this type of experiment. Basically, just X and Y. Dependent and independent variable. If you're trying to remember which one X and which one Y is when you're doing statistics, the explanatory variable, explanatory, right? Which one explains why the other one is the way it is. So X explains why the other one is. So explanatory versus the XY. Anyway, I'll have you keep track of it maybe when you're doing scatter plot charts. And then dependent depends on other things to influence it. Independent independently has the effect on the dependent variable and does not have an effect on the other independent variables in the experiment. All right, I got a little sidetracked there. Let's go around to the types of control: negative control, positive control. So when nothing is expected, when you expect whatever it is to do to not be harmful, you're looking to ensure that there is no effect. Like, for example, is this drug showing any kind of adverse reaction? Are people having allergic reactions to it, right? So you're controlling for the negative, you're expecting there to be no effect, and then when there is, then you can show that, or you can infer that a confounding variable acted on it. Positive controls, you're looking for a positive effect of some kind, an effect when there should be an effect, right? The effect doesn't have to be negative. When we think of negative, we think of bad or harmful, but negative would mean no effect. So we expect no effect. We did have an effect. Something else is influencing it. We're expecting an effect to happen, and there is an effect versus not having an effect. We can draw conclusions from that. So that is about that. Again, this is just meant to be a brief overview, not me reading the entire chapter to you. So make sure that you check all that out before you do your quiz. And then as you get on with your Excel challenge, you just need to click the drop down here would be the best way to do it, and then go through each of the 4 sections. The video I've recorded and uploaded will walk you through the entire chapter practice, and then when you're ready, you'll do the entire chapter scored. And again, the video will go through that, but you'll just download the Excel file, the data file that it gives you, and then complete that and make sure you submit that to the spot on Blackboard. Thanks everyone. We'll see you in the next chapter.